Chemical reactions shuffle electrons, but nuclear fusion reshapes the heart of matter. By merging light nuclei, we access the strong nuclear force, releasing energy millions of times greater than burning fossil fuels. Every liter of seawater contains 33 milligrams of deuterium. This isotope occurs naturally and is virtually inexhaustible, providing a potential energy source that could power human civilization for billions of years. Tritium contains 1 proton and 2 neutrons. Unlike stable deuterium, tritium is radioactive, with a half-life of 12.3 years and is rarely found in nature due to its rapid decay. When deuterium and tritium fuse, they form an unstable helium-5 intermediate. This state immediately decays into a highly energetic helium-4 nucleus and a high-speed free neutron. The reaction releases 17.6 mega-electron-volts of energy. 80% is carried by the neutron, while 20% remains with the helium nucleus, also known as an alpha particle. Positive nuclei naturally repel each other via the Coulomb force. To fuse, they must overcome this electrostatic barrier, requiring extreme velocities and temperatures exceeding 100 million degrees Celsius. At lower energies than the classical barrier, fusion still occurs through quantum tunneling. Particles have a statistical probability of appearing on the other side of the potential barrier without climbing over it. The cross-section measures the probability of a fusion event. The Deuterium-Tritium reaction has a much larger cross-section at lower temperatures compared to other fusion fuel cycles, like proton-boron. At fusion temperatures, electrons are stripped from nuclei, creating a plasma. This collection of charged ions and free electrons behaves as a conductive fluid governed by electromagnetic fields. Plasmas exhibit Debye shielding, where charged particles rearrange themselves to screen out electric fields. This collective behavior distinguishes a true plasma from a simple ionized gas. For net energy gain, the plasma must satisfy the Lawson criterion. This requires a specific product of plasma density, temperature, and energy confinement time to reach ignition. The triple product is the modern metric for fusion progress. It combines ion density, temperature, and confinement time to determine how close a machine is to self-sustaining fusion. Since no physical material can withstand fusion temperatures, we use magnetic fields to confine the plasma. Charged particles are forced to follow helical paths along magnetic field lines. The Lorentz force acts perpendicular to both particle velocity and the magnetic field. This causes ions to orbit the field lines with a radius determined by their mass and charge. The tokamak uses a donut-shaped vacuum vessel called a torus. Large external coils produce a toroidal magnetic field that wraps around the vessel to keep the plasma off the walls. A purely toroidal field leads to particle drift and loss of confinement. By inducing a current in the plasma itself, we create a poloidal field that twists the overall magnetic field. The central solenoid acts as a primary transformer winding. Increasing the current in this coil induces a massive current in the plasma, which provides both heating and confinement stability. Plasma current heats the fuel through resistance, known as ohmic heating. However, as the plasma gets hotter, its resistance drops, making this method insufficient for reaching fusion temperatures alone. To reach higher temperatures, we shoot high-energy neutral atoms into the plasma. These atoms are not affected by magnetic fields until they collide and ionize, transferring their kinetic energy. Microwaves tuned to the natural frequency of the ions or electrons can also provide heat. This resonance heating transfers electromagnetic energy directly into the orbital motion of the particles. Stellarators provide the necessary magnetic twist using complex three-dimensionally shaped coils. This allows for steady-state operation without the need for a continuous plasma current like a tokamak. Inertial confinement uses powerful lasers to compress a fuel pellet. The outward ablation of the outer layer creates a rocket-like inward force that crushes the fuel to extreme densities. In indirect drive fusion, lasers hit a gold cylinder called a Hohlraum. the cylinder emits intense X-rays that compress the fuel capsule more uniformly than direct laser strikes. During compression, small imperfections can grow into instabilities that mix the fuel and prevent ignition. Achieving perfectly symmetric implosions is the primary challenge in inertial fusion energy. Once fusion begins, the resulting alpha particles remain trapped by magnetic fields. They collide with other fuel ions, providing enough heat to maintain the reaction without external power. High-energy neutrons carry 80% of the fusion energy and escape the magnetic field. They are captured in a surrounding blanket, where their kinetic energy is converted into heat. The blanket contains lithium, which reacts with the incoming neutrons to produce new tritium fuel. This closed fuel cycle ensures a continuous supply of tritium, despite its short half-life. Intense neutron bombardment displaces atoms in the reactor structure, leading to material swelling and brittleness. Managing this structural damage is critical for the long-term operation of fusion plants. The first wall must withstand extreme heat and particle fluxes. Tungsten is often used due to its high melting point and low retention of the hydrogen isotopes used as fuel. Helium produced by fusion acts as an ash that can dilute the fuel. The diverter uses specialized magnetic fields to pull this ash out of the plasma and into a pumping system. To create powerful magnetic fields efficiently, we use superconducting magnets cooled to near absolute zero. These magnets allow for huge currents with zero electrical resistance and minimal power loss. Disruptions are sudden losses of plasma confinement that can damage the reactor wall. Scientists use fast gas injection or frozen pellets to safely quench the plasma before it strikes. The ratio of fusion power produced to the heating power injected is called the Q factor. Scientific breakeven is reached at a Q of 1, where output equals input. Total plant gain must account for the efficiency of the lasers, magnets, and turbines. A reactor needs a physics Q of over 30 to achieve a net gain for the electricity grid. Heat generated in the lithium blanket is carried away by a coolant, like pressurized water or helium. This heat drives a conventional steam turbine to produce electricity for the grid. Even tiny amounts of impurities, like oxygen or carbon, can cool the plasma through radiation losses. Heavy pumping systems maintain a vacuum 10 billion times thinner than the atmosphere. The cryostat is a massive vacuum-insulated vessel that houses the superconducting magnets. It maintains the extreme temperature gradient between the million-degree plasma and the liquid helium-cooled coils. Scientists monitor the plasma using lasers and cameras. Thomson scattering measures electron temperature by observing how laser light reflects off the high-speed particles within the core. Free electrons radiating energy as they curve around ions cause bremsstrahlung radiation. These losses increase with the square of the atomic number, making high-purity fuel essential for performance. Beta is the ratio of plasma pressure to magnetic pressure. Higher beta values mean we can confine more fuel with less magnetic field, increasing the overall efficiency of the reactor design. The International Thermonuclear Experimental Reactor is a global effort to demonstrate a Q of 10. It is the largest and most complex scientific instrument ever constructed by humanity. Unlike fission, fusion cannot have a runaway chain reaction. If the fuel supply is interrupted or the confinement fails, the plasma cools and the reaction stops in seconds. Fusion does not produce long-lived radioactive actinides. The primary waste is the activated reactor structure, which becomes safe to handle within 100 years through careful material selection. Lithium is abundant in Earth's crust and can even be extracted from seawater. A single laptop battery worth of lithium provides enough fuel for one person's lifetime energy needs. Earlier fusion designs used magnetic mirrors with stronger fields at the ends to reflect particles back. While they suffered from too many losses, they paved the way for modern confinement theory. Aneutronic fusion could allow for direct conversion of charged particle energy into electricity using electrostatic deceleration. This avoids the heat losses associated with traditional steam cycles and turbines. New high-temperature superconductors allow for much stronger magnetic fields in smaller devices. This shift toward compact tokamaks could significantly accelerate the timeline to commercial fusion power. Plasmas can generate their own internal current through pressure gradients, known as the bootstrap current. High bootstrap fractions reduce the need for external current drive, making steady-state operation easier. Spherical tokamaks resemble a cored apple rather than a donut. This shape allows for higher plasma pressure relative to the magnetic field, improving the efficiency of the confinement. Neutral atoms can penetrate deep into the plasma before ionizing. Modeling their transport is essential for understanding how the fuel is fueled and how heat reaches the reactor walls. Periodic bursts of energy, called edge-localized modes, can erode the reactor surfaces. Scientists use magnetic perturbations to trigger smaller, frequent pulses that do not damage the wall materials. The tritium and deuterium must be ultra-pure before injection. Cryogenic distillation columns separate the isotopes based on their boiling points to ensure the highest possible fusion reactivity. Surfaces cooled to below 20 Kelvin can freeze out gases, creating a powerful vacuum. These cryopumps are used to handle the massive gas loads required during long fusion pulses. Fusion provides energy density millions of times higher than chemical fuels. A single gram of deuterium-tritium fuel yields as much energy as 11 tons of coal without the ash. After experiments prove net energy gain, the next step is demo. This demonstration reactor will be the first to actually supply hundreds of megawatts of electricity to the commercial grid. Fusion represents the ultimate energy source, utilizing the same process that powers the stars. Its development promises a sustainable, clean, and nearly limitless energy future for all of human civilization.